So the pressure that the ventilator needs to use would be required to overcome, number one, the resistance, and number two, the flow, or it would be related to the flow that we would be using on the ventilator. And then we need to overcome the elastance of the lungs and the chest wall. And you know that the elastance is the reverse of the compliance. So the higher the elastance, the higher the pressure that I need to utilize. So since it is the reverse of the compliance, I can put the compliance here in the denominator. Okay. And then if I need to push more volume into the lungs, that means I'm going to utilize more pressure. So that the volume would be related directly, or the pressure will be related directly to the volume. The higher the volume that I need to get into the lungs, the higher the pressure that is utilized. Now, the pressure that is on the ventilator is actually variable based on how much the patient is going to participate also. Okay. And the pressure would be not only the ventilator pressure, but also the muscular pressure that is generated by the contraction of the respiratory muscles. So you need to combine these two pressures together in order to push that air into the lungs. Now let's just take a scenario how this is changed. Okay. In volume controlled mode of ventilation, in volume controlled, that means that we are controlling the volume here. So let's say that I have a mode that I need to deliver 500 ml of tidal volume. This is the control, it's fixed. So this is the independent variable. Now, the equation of motion has to be equal on both sides. In order to deliver the 500 ml, the machine will utilize pressure. That pressure is dependent on, number one, how much resistance do we have? And number two, what is the flow that you're going to utilize? And number three, what is the compliance of the lungs and the chest wall? Now, the lower the compliance, the higher the pressure that we need. The higher the resistance, the higher the pressure that we need. The higher the flow, the higher the pressure that we need. And since this is a volume control, the patient can breathe. So he can participate in the generation of the pressure. And if the patient generated the pressure here, the ventilator pressure will go down. The difference between or the sum of the ventilator pressure and the muscular pressure or the patient's pressure would actually be equal to resistance multiplied by flow plus volume divided by compliance. So let's get the ventilator and apply this formula on the ventilator. Let me share my screen. Okay. So what I'm going to do, I'm going to simulate what we just did with the equation of motion. I said that we want to deliver 500. So this is 500. And we're going to control the volume. That means volume control mode of ventilation. I'm going to give this 500 at 30 liters per minute. And I'm going to decide that I'm going to do this in 1.5 seconds. So you can see that the ventilator gives the pressure. This initial rise in the pressure is the pressure required to overcome the airway resistance. And then there's a steady increase in the pressure. This is to overcome the lung elastance. We started getting air into the lungs and the chest wall elastance. The peak inspiratory pressure is the pressure required to overcome both airway resistance, lung and chest wall elastance. Now, since I wanted to get 500 in and I set the flow at 30 liters per minute, I can get the 500 in 1 second only. The flow of 30 liters per minute would deliver 500 in 1 second. However, inspiration is not ended yet. The inspiratory time is 1.5 seconds. Thus, there is a period of inspiration that there is no need to move any air into it. We call this the plateau phase. And in order to, but the air is inside the lungs. In order to keep the air inside the lungs, we need to utilize pressure. That pressure is required to overcome the lungs and the chest wall elastance. And you see that the flow is 0 here. Okay, so let's try to change those variables that we talked about. The first thing, I'm going to increase the resistance. And you can notice the pressure right now is we have a peak pressure of 14 and plateau pressure of 10. So I'm going to increase the resistance, and I'm going to do it after the first breath here. So by increasing the resistance, on one side of the equation, the resistance is increased, thus the pressure is increased on the left side of the equation. And which pressure increased? The initial rise in the pressure, the airway pressure. Okay, at the same time, the peak pressure would be increased. The difference between the peak inspiratory pressure and the plateau pressure is increased. However, the plateau pressure is the same. So we know that the problem is in the airways, and we had to utilize a higher airway pressure in order to deliver that 500 in. So this is the first thing that would dictate the change in the pressure. Let's go down on the resistance again. Okay, so we're back lower on the pressure since the resistance is improved. The next thing I'm going to change is the flow. So as I said, the pressure required to deliver the air is related to number one, the resistance, and number two, the flow. So I'm going to go up on the flow. I'm going to double that flow from 30 liters to 60 liters. And I want one of you to tell me what happened. I'm going to freeze it here. And any volunteer to tell me what is the difference between the second breath here and the first breath. You can raise your hand or you can unmute yourself and just read it.
So the peak airway pressure increased and the plateau phase increased.
Okay, thank you, Ali. But always, Ali, start from the beginning of the breath. You jump to the peak inspiratory pressure. Did you notice anything different here? Yeah.
So because we increase the flow, so now the air is delivered in a shorter time. So the angle of the, so the pressure went just high, rapidly rather than the.
Excellent. So the airway pressure is increased. So let's just say, keep yourself unmute so we can interact. So the initial rise is the airway pressure. And this is certainly related to the flow. The flow is doubled, so the pressure is increased. So the airway pressure is increased remarkably. Okay. Now, the peak inspiratory pressure is increased at the same time. Okay. However, it doesn't look like the slope slightly higher because you're doing it shorter, actually, in shorter time here. So the slope of the pressure will actually go higher a little bit, and you can notice this. Okay, so the main thing is the peak inspiratory pressure and the airway pressure are both increased. However, the plateau pressure is not, right?
Correct.
Okay, so why are you saying that this is because of the flow and it is not because of airway resistance?
Because like the more because the higher the flow, the higher the pressure, as per the equation.
And the higher the resistance, the higher the pressure too.
Correct.
Okay, so how can you say that this is, you see the flow, yes, but how can you say that this is not associated with increased resistance at the same time?
Like we can look into the other the expiration went smooth, so it's
Excellent.
there is no auto beeping.
Excellent. So take a look on expiration. So if it was a resistance problem, it would be reflected on the expiration. Resistance meaning there is limitation of the flow. What you see here is the expiratory phase is exactly the same as the previous one here. So if it was a high resistance here, it should have actually affected the expiration also. The expiration is happening exactly similar to the previous one, meaning that there is no change in the airway resistance. Let me go back and show you the difference. Why do we have a longer plateau pressure or plateau phase?
Because the desired volume was already delivered in a shorter
Excellent.
period, so we have more time in the inspiratory time.
Okay, and the cycling mechanism is 1.5 seconds. That's not changed, so we have more time in inspiration for the plateau. Okay, so let me go back and show you the resistance again and how it's affecting the expiration. So this is back to 30 liters per minute now, and I'm going to increase the resistance and freeze it for you. Okay, so Ali, can you see the difference now?
Yes, it's so clear now.
Okay, you can see that, well, it's the same thing here. Look at the initial rise, it's increased. The peak pressure is increased. Difference between peak pressure and plateau is increased. Okay, so I can see here that the flow is not different than the one before. Okay, but the more obvious thing for you is to compare the expiratory flow. You can see, number one, the peak expiratory flow is less compared to the initial one here. And number two, the slope of the expiration is shallower. You can see how it's like going slowly here. Look at this, how steeper it is. Okay. And number three, look at the duration. The expiratory flow duration is longer than the previous one. And at the same time, you can notice that there is probably persistent flow at end of expiration, which is auto beep. Thank you very much, Ali. So this way you would say, well, the increase in the pressure that I see here on the ventilator is related to the airway resistance, is not related to the flow. Okay, however, and let me just show you, you can have both at the same time. Of course, I'm just manipulating the ventilator for you to understand. I can actually have airway resistance and the flow would be higher. So this is the first one, and look at the second one here. Look at this. So the flow here is higher, and you still see the limitation of flow. Of course, I did not change the resistance, so still you see limitation of the flow here, prolonged duration of the expiratory phase, and persistent flow at end of expiration. Okay, so that's a second variable that if it's changed, the pressure would actually be different. Let's go back and correct this to back to the baseline and improve the resistance. Okay, I need another volunteer, please. And now I'm going to change another variable. Okay, I'll get the first one, the second one, and then the third one. I'm sorry, I have to do it again. Okay, so I'm going to wait for the first breath. And then decrease. Okay, so any volunteer? You can just unmute yourself, and if none, Ali, go ahead.
Okay, so we can see that in the second breath that there is increase in both the peak airway pressure and plateau pressure.
Excellent.
Also so which indicates that there is an issue with the lung compliance.
Okay, so there is increase in the peak pressure and the plateau pressure without increase in the airway pressure. You can see the difference between the peak pressure and the plateau pressure is still the same. So that indicates that the problem is in either in the lungs or in the chest wall, right? At the same time, take a look on the expiratory phase. What do you see in it?
So it's more steep than the previous chart, which means that the issue is mostly is not the resistance. It's mainly the compliance itself.
Exactly. So you can see that the peak expiratory flow is higher. The slope of it is steeper, and you can see the duration is much shorter compared to the previous one, indicates that the lung is stiff. It's just like emptying very fast, and it's pushing the air outside very fast. And this is the reason why the pressure is required higher at a level higher than what it was before. So this way we simulated the equation of motion in both the resistance and the compliance. So let me just add one more thing. I said the pressure that is required from the ventilator is actually dependent on how much the patient is breathing. In all the examples that I showed you, the patient was not breathing on his own. So everything was delivered from the ventilator. So what if the patient started to breathe on his own? See what happens. Okay, so for the same example here, now the patient is going to breathe on his own. What will happen is the pressure that is going to be utilized is going to be less. And you can see how the pressure here, so this is the patient's initial pressure. This is SIMV now. The pressure from the ventilator would be related. Look at this pressure here, much lower. The pressure from the ventilator will be related to how much the patient is generating. If the patient is generating negative pressure on his own, the ventilator will not have to use much of the pressure in order to deliver the air. So remember, the driving pressure is the tracheal pressure minus the intrathoracic pressure. So this is a transpulmonary pressure. The transpulmonary pressure is the true driving pressure. What you see on the ventilator, the difference between the plateau and the PEEP is the driving pressure. But the true driving pressure is what the patient is doing at the same time. It's the tracheal pressure minus the intrathoracic pressure. And when you see that the pressure dropped like this, that means that the patient started breathing on his own and he delivered, he participated in the breath to deliver the same tidal volume. Any questions so far? Okay, so let's go back to our whiteboard and let me put the equation again. So we have a pressure on the left side that equals resistance multiplied by flow. This is plus volume divided by compliance. So in the first example, we had volume control mode of ventilation. Now we're going to have pressure control mode of ventilation, meaning that we're going to control that pressure at, let's just say, 20 centimeters. Okay. So if we control the pressure at 20 centimeters, now it doesn't matter. The machine will give that 20 centimeter no matter what. This pressure is going to be exactly the same here, regardless whether the patient is breathing or not. So the muscular pressure will be added to this pressure here on the left side. Okay. So now we're fixing the pressure on the left side. Since we are fixing the pressure, we cannot control the flow anymore. So in pressure control mode of ventilation, we don't have a control on the flow, and we'll see how we eliminate that now when we see the simulator. So we have only the resistance and the compliance. So if the pressure is fixed on the left side in the equation of motion, the volume that is generated is dependent only on, number one, the resistance, and number two, the compliance of the lungs and the chest wall. Okay. And the volume is also dependent on how much the patient is contributing to the breath. Because if the patient is generating -10 here, so now the pressure is 20 plus 10. 20 minus -10, that means 20 plus 10, that is 30 centimeter. And that 30 will result in higher tidal volume if the resistance and the compliance stay the same. So the equation of motion in pressure control mode of ventilation, the pressure on the left side is fixed, is determined by the operator, and the volume will be dependent on the resistance and the compliance. Okay, so let's see it. Okay. Any other volunteer? Does anybody want to participate? Okay. So now I'm going to put the patient on a pressure control mode of ventilation, and I'm going to select a pressure of 20 as we decided. I'm going to keep the inspire time the same at 1.5 seconds, beep of 5, and the same other parameters. All right. So with this, I'm going to simulate the changes in the resistance and the compliance. But you can see here first that once we decide to control the pressure, take a look on the flow. We don't have any control for the flow anymore. So this is the pressure, this is inspire time, respiratory rate, PEEP, the ramp, and the pressure support. So we cannot control the flow anymore, and you can see how the flow now is decelerating. It goes to the peak inspiratory flow and decelerates. So it is by default any pressure controlled breath. The flow in that the flow is decelerating wave. I'm sorry. Okay, so let's simulate the increased resistance first. So I'm going to go up on the resistance and see how that is going to be different. So the first breath is going to be with a normal resistance. The second breath is going to be with higher resistance. Okay, go ahead, Ali.
Okay, so because we are in a pressure control mode, so we limit the pressure, so the pressure is the same. However, the delivered volume is less, and also the flow is less.
Okay, excellent. Thank you very much, Ali. So, Ala. So Ali said that since the pressure is the same, we have lower tidal volume, right?
Yes.
You know, let me just redo this because I want it to be clearer. It's not very clear at this point. Let me just do it again, so it will be very clear. Okay. So let's see how much tidal volume for the first one. Okay, so this is the first one. I'm going to increase the resistance here, and I'm going to maybe higher. Okay, now we can see the difference. So let's just compare the third one with the first one, Ala. So Ali already said that it's the same pressure, but the volume is less. What can you tell? What else you can tell me?
Okay. Because we are in the pressure control, so the pressure is the same in the pressure times. The flow expiratory flow is prolonged, and because the volume in the volume times, the volume in the third one, it will be decreased rather than one.
Okay, so in other words, what you're saying is what we see here is same pressure, less tidal volume. Well,
Yeah.
it would be, I don't know whether this is resistance or compliance problem, right?
Yes.
Okay, because if you have a compliance problem, it's going to be the same. The same pressure is going to be given by the machine and less volume. Okay, and that's what you see here. There's no way to know if you look only on the pressure on the volume. Okay, you have to look at the flow, and you can see if you look at the flow even in inspiration. Okay, you can see some limitation. Look at this flow here and compare to the first one. But more obvious would be the expiration. You can see
It's
the
more with the
expiratory.
resistance.
Excellent. So you see the peak expiratory flow is much less here. The slope of the expiration is very shallow compared to the previous one here. And the duration of expiration is longer. And maybe there's some persistent flow at the end of expiration. So that actually tells you that the problem is in resistance, not in compliance, right? So stay with me, Ala, and yeah, Ala, let me just get back to normal, and then we can actually simulate the other one. Okay, so this is back to normal now, and I'm going to decrease the compliance. If you decrease the compliance, tell me what happens, Ala.
Okay, because we are in the pressure control, so the pressure is the same. But in the second wave, in the flow time, the second one, it is the shorter the expiratory flow. The peak expiratory flow is the shorter rather than the first one. And even the volume time in the third wave, it become less, which is going with the compliance rather than resistance.
Excellent. So it's the same pressure that is given. Again, equation of motion, pressure on the left side is fixed. Now on the right side, we see less tidal volume. This could be either because of the resistance increased or the compliance decreased. For in this example here, if you compare the flow in inspiration and expiration, you can see that the expiratory flow is higher. The slope is much steeper compared to the previous one. And look at the duration of expiration. It's very short. So it's shorter than the first one, indicating that the lung is very stiff, and the problem is in the compliance, it's not in the resistance. Okay, and the last thing actually in this equation of motion here, what if the patient started to breathe here? What happens to the tidal volume, Ala?
يعني if the patient has started to the breathe,
Yeah.
the tidal volume, because we have a compliance is very low, so the compliance, the tidal volume will be less.
Think about it again. Think about it again, Ala. The patient started to breathe here. Okay. The machine will give the same pressure. If the patient started to breathe at the same time, what happens to the transpulmonary pressure?
The transpulmonary pressure will be increased.
Okay, if it is increased, what happens to the volume?
The volume will be increased.
Excellent. Thank you very much. That is correct. Any question? So for you as intensivist, it is really important that you understand this equation here. Okay, you cannot understand mechanical ventilation without full understanding of the equation of motion. The pressure on the left side equals resistance multiplied by flow plus volume divided by compliance. In volume control mode of ventilation, we control, let me just stop the simulator. In volume control mode of ventilation, we control the volume, and this is the independent factor or variable. Now, the pressure that is utilized by the machine is dependent on number one, the resistance, number two, the flow, number three, the compliance. The higher the resistance, the higher the flow, the lower the compliance, the higher the pressure that is required. In pressure control mode of ventilation, the pressure is fixed, and this is the independent variable. The volume will be dependent on the resistance and the compliance. We cannot control the flow anymore. The higher the resistance, the lower the compliance, the lower the tidal volume that is generated with the same pressure. Another component that you need to take into consideration is the patient's ability to breathe. In pressure control ventilation, if the patient started to breathe, that pressure will be added to the pressure that is set on the machine. Thus, the volume will be higher. In volume control mode of ventilation, that pressure will be contributing to the volume with the machine pressure. So the machine pressure will go down if the patient started to breathe on his own. So the pressure will be variable to give the same tidal volume. If the patient is breathing with the machine, there is no need for higher pressure of the machine, and then the pressure will be lower. Now, any questions so far? We're almost done, but I had a question regarding the time constant. Grace, you can actually see if there are any questions coming to the chat section. But I can see here a question: how can we correlate time constant with equation of motion? Well, let me just show you time constant. The time constant has nothing to do with the equation of motion, but let me just write it for you first, and then we can simulate it. The time constant is the time required. It's the other way around, actually. No, let me get a new board. The time constant is the time required to deliver or exhale 2/3 of the air. And it's usually related to resistance multiplied by compliance. Okay, so let me see if I can, if I have an inhaled volume here and I'm exhaling now. Okay, so the time constant will be the first 2/3 of the air. So the 2/3 of the air, how much time did it take? Let's just say it took 0.5 seconds, okay, to exhale 2/3. So it took 0.5 seconds to exhale 2/3 of the air. Now it will take, to exhale the rest, it will take 4 times the time constant. So that means 0.5 multiplied by 4. So that's 2 seconds. 4 times the time constant. Okay. So in increased resistance, you would require a longer time constant, a longer expiration. In decreased compliance, you would require shorter time constant. Let me simulate this for you and you can understand it in a better way. So first I'm going to show you a normal time constant. Okay. So I'm going to put the patient on CMV mode of ventilation. Same parameters so you don't get confused. 30 liters and 1.5 second. All right. So again, the time constant is the time that is required or the time that elapsed for the exhalation of 2/3 of the air. So you can see this is a peak expiratory flow. 2/3 of it would be here. That would be the time constant. This is the time that is required to exhale 2/3 of the air. In order to empty the air completely from the lungs, you would require 3 to 4 times the time constant. So it would be a long expiration to exhale the remaining 1/3 of the air. Now, the time constant is resistance multiplied by compliance. So if I increase the resistance, and I will do it after the first one, the time constant is increased. So that's the first one. I'm going to increase the resistance here. And you can see, actually it happened here. So let me just do it again. Okay. So you can see that the time constant here is shorter than what it is here. Look at the 2/3 of the air is actually exhaled in longer time compared to the previous one. So this is what happens with increased resistance. Increased resistance will increase time constant, so it would require a longer time for expiration. And you know, those patients with asthma, the ones who have increased resistance, they come to you with prolonged expiration. They come to you with prolonged time constant. They would need a long time before they can exhale everything in the lungs. And if they become very apprehensive and they are tachypnic, they don't have time to exhale everything. They come to you with inhaled or inflated lungs because of the auto beep that they have. Now, when we ventilate those patients on the ventilator, we need to account for the increased time constant, so we don't cause the auto beep or the dynamic hyperinflation. Similarly, or the other way around, in compliance, it's going to be less time constant. So this is back to normal time constant, and you can see here it's shorter than when it was with increased resistance. Now, when I decrease the compliance, now the lung is stiff and it's going to exhale faster. And you can see 2/3 of the air were actually exhaled in less time compared, look at the third one here. 2/3 of the air exhaled in less time compared to the first one. This is due to decreased compliance. And this is a shortened time constant. Any question? Ala,
there's a question
you want?
in the chat from Ahmed. What's the significance of drive pressure?
The significance of driving pressure is actually the most important pressure that you need to monitor on the ventilator. The driving pressure, again, is plateau pressure minus PEEP. You want this to be less than 18 centimeters of water. Better if it is less than 15 centimeters of water. This will cause less lung injury and it will provide safer mechanical ventilation on the injured lungs. Okay. You need to take into account the true driving pressure. Again, the true driving pressure is what the patient is generating at the same time, combined with the pressure from the ventilator. So that would be the plateau pressure minus the intrathoracic pressure that you cannot measure unless you have an esophageal catheter placed in the patient. Thank you for the question.